So focusing on the BIC for model selection, let's imagine that we have R different candidate models, M1 through MR. So they could be a Gaussian mixture with one Gaussian up to a Gaussian mixture with R Gaussians, or an HMM with one state versus two states up to R states. Let's also imagine that we have data. We're going to call that D, which is n observations x1 through xn. And now what we want with the BIC, the starting motivation is that we want to find the posterior distribution on each of the models. So for the ith model, we want to find the posterior distribution of the model I given the data. And so what this is asking in using Bayes' rule is for us to calculate the likelihood of the data given the model times a prior on the model divided by a sum of the numerator overall of the different models. And this way, we're getting a posterior distribution on our models. We're not getting a posterior distribution on their parameters, but we're actually getting a posterior distribution on the model itself. So this is saying a posteriori, which model do I think generated this data? So from the standpoint of motivating the BIC, we're going to assume that each model has a uniform prior, that a priori we aren't biased towards any model. They're all equally probable. And then because the denominator is simply a normalizing constant, what we can then say is that by finding the most probable model, we want to find the argmax of the log likelihood of the data given each model. So this is we pick model I, we calculate the log likelihood of the data given that model, and then we're going to pick the most probable model according to that likelihood to tell us which is the model order that we should select. And so notice that there are no model parameters here. So where they've gone is indicated by this integral. Actually, by writing the log likelihood of the data given the model that we've chosen, what we're really saying is that we want to calculate the log likelihood of the data given the model and a particular parameter setting times the prior of that parameter setting given the model, and then integrated over all possible model parameter settings. So for example, if MI is a Gaussian mixture model with I Gaussians, MI simply indicates that that is the model that's chosen, a Gaussian mixture model with I Gaussians. Theta then would actually contain the parameters for that I Gaussian mixture model. It would contain the I different means, the I different covariances, and the I-dimensional probability distribution on those I Gaussians. So all of the model parameters would be contained in theta. We define some prior probability on those parameters, and then we integrate them out. And I apologize, this integral should be inside of the log. So what we're choosing with the BIC, in principle, is the model with the largest marginal likelihood of the data by integrating out all of the model parameters. However, this is, in almost all cases, not an integral that we can solve, and so we have to come up with some sort of an approximation. And we'll see how the BIC criterion arises by making an approximation of this log marginal likelihood of a data set given the model class as equal to the log likelihood of the data given the maximum likelihood parameter setting of the model and given the model class, the model order, minus the BIC penalty, minus 1/2 times k times the log of the number of observations. So the BIC is a mathematical technique that motivates approximating this log marginal likelihood by this sum of the log likelihood given the maximum likelihood parameter setting and this additional penalty that we're going to pay for the model complexity of the ith model. So in the remainder of the lecture, I want to simply show why this value can be approximated by this value, in which case if we replace our goal of picking the best model according to this marginal likelihood with picking the best model according to this value, we simply have to find the maximum likelihood parameter setting for each of the models that we're checking over, and then add the appropriate penalty for the model complexity. So first, let's notice that the difficulty is with the integral. So I'm rewriting the integral with the correct ordering here, where we say that the log of the likelihood of a data set given the model order, given the particular model that's chosen, is equal to the log of the integral of the data given a parameter setting times the prior probability of that parameter setting that we define. And so in here, again, both of these probabilities are going to be conditioned on MI as well, the model that we've actually chosen, but in the rest of the lecture I'm going to suppress the conditioning on the model. So when you see this likelihood and this prior, what's implied is that we've actually picked a model to begin with. We've picked, for example, an I-Gaussian mixture model, and then this is the appropriate prior on the parameters of that model. And we've also, in picking an I-Gaussian mixture model, this is the appropriate likelihood of a data set coming from that model. So what we're going to do is very similar to what we did with the Laplace approximation towards the beginning of the course. We're going to approximate this integral using a second-order Taylor expansion. So let's work through the steps of deriving the BIC. Again, remember that what we want to do is calculate the log of the marginal likelihood of the data given the model, and we're going to write that as the log of an integral over the likelihood of the data given a model parameter setting theta times the prior probability of theta that we are going to define, integrated over theta. So this is the marginal likelihood of a data set represented as an integral over the model parameters. And then we're going to replace this likelihood of the data given theta with an equivalent representation of the exponential of the log of that likelihood. So of course, this term is equal to this term because the exponential and the log cancel out. However, when we represent it this way, we can then approximate the log of the likelihood using a second-order Taylor expansion. So if you'll recall in an earlier lecture when we discussed the Laplace approximation, we did something very similar to this. So our goal now is to take the log of the likelihood of the data given model parameter setting theta and approximate this with a second-order Taylor expansion. And we get to pick any point to approximate this, function at, but we're going to pick the maximum likelihood point. So if of course, if our objective is non-convex, we can't necessarily say we found the maximum likelihood solution, so we could run the algorithm multiple times at multiple starting points and pick the best solution that we get. Each time it'll converge to a mode. It won't necessarily be the best solution. However, we can pick the best one and then call that the maximum likelihood solution. So we find a value for theta at a mode and call that the maximum likelihood solution. And we now approximate the log of the likelihood of d given theta with the log of the likelihood of d given evaluated at the maximum likelihood solution, plus a first-order term, which notice is a free parameter of theta, and in both of these two locations we evaluate the gradient at the maximum likelihood solution, and we take the difference of theta with the maximum likelihood solution here, plus a second-order term, which is 1/2 times the difference of theta from the maximum likelihood solution on these two sides, and here we have this, the matrix of second derivatives of the log of the likelihood evaluated at the maximum likelihood solution. So these two terms are free functions of theta, and this term is a constant, and everywhere else we're evaluating theta using the maximum likelihood solution. So notice that by evaluating this at the maximum likelihood solution, we can cancel out this term because the gradient at that location is equal to 0, and so this term goes away, and we're left with these two terms. And now this matrix I'm going to call negative j, and it's going to be a function of the maximum likelihood solution. So I'm going to call this shorthand negative j. Then if I take my log likelihood in this integral and I replace it with these two terms, what I find is that I can approximate the log likelihood of a data set given a model by the log likelihood of the data set where I evaluate that model at the maximum likelihood solution, plus the log of this integral. So that I found this approximation by simply approximating this log likelihood with these two terms. Plugging them in, I get that this is approximately equal to this. So now let's look a little bit closer at the integral that we have to evaluate, at this integral here. We notice, and this is exactly what we saw with the Laplace approximation as well, that this integral is simply the normalizing constant for a multivariate Gaussian with mean equal to the maximum likelihood parameter setting and precision matrix equal to J, this matrix of second derivatives. Therefore, we can say that this integral is equal to 2 pi divided by the determinant of the matrix J raised to the power k divided by 2. And so where's k coming from? Remember, theta is every single model parameter, scalar, one-dimensional parameter in our model that we can freely change. So for a Gaussian mixture model, we have all of the means and covariances for the different Gaussians, as well as the dimension as the distribution on those Gaussians. So theta is a set of many different parameters, and we're mathematically approximating that with this Gaussian, even though, if you'll recall, with the Laplace approximation, we motivated not doing that. We're actually not going to do this in practice. It's just a mathematical construction. So theta can be very high dimensional. This could be a several thousand dimensional multivariate Gaussian, but it's okay because we're never actually going to calculate any of these things. Or I should say, we're never going to have to calculate this huge precision matrix. Okay, so that's where this k is coming from, because we have k different model parameters in this vector theta. Now let's remember our definition that negative j is equal to the second derivative of the log of the likelihood evaluated at the maximum likelihood solution. So because, and this is going back to the beginning of the lecture, we are making the assumption that our n observations are generated IID from this model on the data, we can write the log of the likelihood of the data as the sum. So I'm doing two things here. We can write this as being equal to the sum over each observation of the matrix of second derivatives of the log of the likelihood of each individual observation evaluated at the maximum likelihood solution. So originally we can say this is equal to this, but then if we multiply and divide by n, we can then say that this term is converging to something as n goes to infinity. So notice we've simply done a trick here. We've multiplied and divided by n, so these two things cancel out. However, if we now focus only on this sum of matrices divided by n, we're seeing that we have a sum of n things divided by n, and what we can show, which we won't prove in this course, but what we can show is that this converges to a matrix as n goes to infinity. And so we have n out here times a matrix that's converging as n increases. So we can wrap this up now by simply plugging it all back in. So we take the log of the likelihood, of the marginal likelihood of the data given the model, and we approximate that as the log of the likelihood of the data evaluated at the maximum likelihood solution, plus, and then here's where we had the integral, the log of the integral, which was the log of the marginalizing constant of a multivariate Gaussian. So the penalty now is the log of 2 pi over the determinant of j raised to the k divided by 2 power. And so remember, if we have the log of a value raised to a power, we can simply bring this out front and divide and multiply by k over 2. And then notice what's going on with this term. So I'll write it out to be more clear. So this term is equal to k over 2 times the log of 2 pi minus k over 2 times the log of the determinant of j evaluated at the maximum likelihood solution. So I've simply taken this value and expanded it out like this. Now notice a couple things. First, as the number of observations increases, this thing is not increasing very quickly, so what we're going to do is simply ignore this term. And now notice what we can say here, that this determinant is equal to n times the determinant of this average matrix, where we sum the matrix of second derivatives over each observation, and then we divide by the number of observations. And so this is a matrix that's converging, and so we can further set this to be equal to minus k over 2 times log n minus k over 2 log times the gradient of, and then 1 over n, and then I have a sum of n items here, like this. Okay, so I now have taken this one term and broken it into a sum of 3 terms, where I have this term minus this term minus this term. I've already gotten rid of this term. And now notice that as n increases, this term is converging as well. It's not increasing very fast. So these two terms are growing order 1 in n as the number of data points increases. And now we are left with only this term, which is increasing in n as n increases. So finally, what we get at is that we've shown, by using the second order Taylor expansion, we can approximate the log of the marginal likelihood of a data set given a model choice as being equal to the log of the likelihood of the data set evaluated at the maximum likelihood parameter setting for that model, minus 1/2 times k over 2 times the log n, plus something that's not growing in n, so something that's order 1 in n. And so this is where the BIC makes a second assumption. The first is using the Laplace approximation. The second approximation is saying that since it's not growing in n, even though it's growing in k, I only care about how it grows in n, and so I'm going to ignore this term and arrive at my final approximation, which is something that's growing, which is a penalty that grows in both k and grows in n. And so we see that this additional penalty that we're going to pay is motivated by a Laplace approximation, which is like a Gaussian approximation on our model parameters.